So what we're doing today, we're starting chapter 8. So chapter 8 goes perfectly right after chapter 7, because basically what we're doing with chapter 8 is the opposite of what we did in chapter 7. So in chapter 7, we learned how to go from x plus 2 times 2x plus 1, where we learned how to FOIL that together, and we said that's 2x squared, and we got a single x, and we got a 4x, and we got a 2, and then we combine like terms. Now, we are a long way from this step. This is going to be probably 4 sections in to get to this step. But the basic goal of this entire chapter, in chapter 7, we went from here to here. I gave you this, you give me this. Chapter 8, I'm going to give you this. We have to learn how to go back and basically unmultiply those together. Figure out what were the things that multiplied together to get that. That's basically the entire chapter. Okay? Now, we're a long way from that. Okay? Today, all we want to talk about first is, we have to talk about prime factorization. Okay? Anybody know what prime numbers are? 2 is a prime number. 4 is not a prime number. What are prime numbers? No. 2 is a prime number. 5 is a prime number. 7 is a prime number. 9 is not a prime number. 13 is a prime number. You missed a couple.
I know, I'm thinking, like 8.
8 is not a prime number. 3 is a prime number. 11 is a prime number. 17 is a prime number. 21 is not a prime number. 19 is a prime number. 23 is a prime number. 27 is not a prime number. 29 is a prime number. Now, here's what this is. Prime numbers are numbers that the only way you can get to a 2 is 2 times 1. There are no other multiplication problems with whole numbers that equal 2. The only way to get to a 3 is 3 times 1. Why is 4 not a prime number? Because 2 times 2 is 4, right? There is a way to get to 4 with other numbers. So 4 is what is known as a composite. A composite number are numbers like 4, 6, 8, 9, 10. Because how can I get to a 4? 2 times 2. How can I get to a 6? 3 times 2. How can I get to an 8? 4 times 2. How can I get to a 9? 3 times 3. 5 times 2. Right? There's other ways to get to those numbers. So prime numbers are numbers that are only divisible by 1 in itself. Okay? I know that 25 is a composite number because I can do 25 divided by 5 and I get a nice number. Right? Because 5 times 5 is 25. That's what makes a composite number. Okay? Now, what we want to do right now is prime factorization. We want to take a number like 24. 24, we want to figure out what numbers multiply together to get 24. But what we want is we want only prime numbers. Okay? Abby, you're going to want to pay attention to this. Now, there's two different ways you can do this. Okay? Now, I like what's known as a factor tree. Okay? To me, the best method is what's known, I like the factor tree. Okay? Because it ends up looking like a tree. And it's actually quite simple. Find any two numbers that multiply together to get 24. Any two, doesn't matter. 2 and 2 times 12, or 12 times 2. Yes? Yeah. Okay. Is 2 a prime number? Yeah, so I can stop them. That to me is a leaf of the tree. You stop at that point. But the 12, that's not, you can go farther. 12 can be broken up into 6 and 2. Now again, that 2 is done. This 6 is not. What can this 6 be broken down into? 3 and 2. Now, the prime factorization is, what do you have now? How many 2's do we have? We have 3 2's, and we have 1 3. This is the prime factorization. Now, does it matter? We started out with 2 and 12. Could I have started out with 8 and 3? Because 8 times 3 is 24, right? Well, 3 is done. I can't go any farther. What about the 8? 4 and 2. The 2 is done. And I keep going. I go 2 and 2. And again, I end up with 3 2's and a 3. When it comes to the factor tree, do we care about the 8 anymore? No. The reason I like to think of it as a tree is I think of it as branches and leaves. In the end, we only care about the leaves of the tree. We don't care about the branches anymore. This branch turned into the 4 and the 2. The 4 we don't care about because the 4 turned into the 2 and the 2. So the 8 and the 4's, we don't care about those numbers anymore. We only care about the end result. To me, this is the best method because it doesn't even matter if you pick prime numbers. If you take 24, we could have done 4 and 6, couldn't we? 4 times 6 is 24. Can we break down this 4 into 2 and 2? The 6 can also be broken down into 2 and 3. What do we end up with? We end up with 3 2's and a 3. We end up with the same thing. We don't even have to find prime numbers to multiply together. Now, there is another method of doing this. It's called the ladder method. Okay? Now, some people like the ladder method a little bit better. I personally don't. Okay? But it ends up being the same. But there's one big difference between the two methods. The ladder method, what you do is you think prime numbers and try to find prime numbers only. What is a prime number that you can divide the 24 by? What is a prime number you can divide 24 by? Well, it's even, so you can divide it by 2, right? So you put a little upside down division sign, and we say we're going to divide by 2. What is 24 divided by 2? 12. Great, now you're at 12. What prime number can I divide the 12 by? I can do another 2, right? I wouldn't want to do 4. Why would I not want to do 4? 4 is not a prime number, right? So the ladder method, you really want to be careful and try not to use composite numbers. You don't want to use numbers like 4 and 6. So 12 divided by 2 is 6. Well, 6 can be divided. What can we divide that by? 2 again, and we get 3. Do we get the same answer? Yes. My personal why I don't like the ladder method as well is that mistake right there of, yeah, I could make that mistake and go 24. All right, I can divide that by 2 and I get 12. I can divide that by 4 and I get 3. Why did I get a different answer here? Because I didn't divide by a prime number, right? So with the ladder method, you really have to be careful to only divide by prime numbers. It works just fine. Okay? It's a really good way of doing things, but you have to be careful that you only worry about prime numbers. With the tree method, you don't have to worry about that at all. All you have to do is come up with any two numbers that multiply together to get the 24. The difficulty here, it's harder to see your answer. Because the mistake a lot of people make with the tree method is they'll get to here, they'll get to this answer and they'll go, all right, I got 3 2s, I got a 3, I got a 4 and a 6. What's wrong with this answer? The 4 and the 6, number one, aren't prime numbers. And did the 4 turn into something else? Yeah, that was a branch of the tree. We don't care about the branches. We only care about the leaves of the tree. So we're not going to ever use those. Those are just how we got there. It's kind of us showing our work. Does that kind of make sense? Let's try another one. How do I do 72? Which method do you guys think you like the best? How many of you like the tree method the best? Okay, I agree. I personally think the tree method is the best way to go. Some people do like the ladder method. And honestly, if you have 10 different math teachers standing in front of you, you're probably going to have 6 of them say, I like the tree method, and 4 of them say they like the ladder method. It doesn't really matter. You can use either method. I personally like the tree method because I don't have to worry about finding prime numbers. I can find any numbers. Now I just think of my multiplication table. Yes, Monday, Wednesday. There's no AAA all week. Yeah, there's no AAA all week. I know. So 8 times 9, yes? Great. Is 8 prime? Or can you break that down farther? You can break it down. What does 8 break down into? 4 and 2. What does 4 break down into? 2 and 2. So you can't break those down. The 9 is 3 and 3. So what's the answer here? I got a bunch of 2s. How many 2s do I have? 3 2s. And 2 3s. Oops. Make sense? Is there a way that I should be able to check your answers here? What should happen with this? It should turn back into 72. If you actually take 2 times 2 times 2, 2 times 2 is 4 times 2 is 8, 3 times 3 is 9, 8 times 9 is 72. It should multiply back together to get the 72. So you absolutely should be able to check those answers. Prime factorization. Have we done this before? What do you think we're doing next? GCF. Now, the next thing we got to talk about is basically the greatest common factor. Now, there's a couple different ways you can do this. Let's say our goal is to find the greatest common factor of 24 and 60. Okay? First off, what is a factor? Something times something equals that, right? So I could, if I wanted to, list all of the factors of 24. What are any two ways I can get to 24? 1 times 24 will get me to 24, right? Those are factors of 24. What else you got? 2 times 12. 3 and 8. 4 and 6. These are all factors of 24. What, Cameron?
How are you standing there other than on that, like outside that brick wall? You're glaring on it. And there's a wall right there.
It's
Literally, I can see
it's a reflection.
Huh?
It's a reflection.
You see, look, you're on that brick. Like, move. Just move around.
Yeah,
See
yeah,
it?
yeah. It's a reflection.
Tell me how. But there's a wall. Like outside of the building, like on in front of Mr. Coley's window, that pillar, you're on there. What? Come here and look.
I don't. Okay, guys, we got stuff to do. Okay, then don't look. Okay, one way to do this. You could list all of the factors. Every single one of these numbers. 1, 2, 3, 4, 6, 8, 12, 24. These are all factors of 24. But then you also got to do 60. What are all the different ways you can get to 60? So these were the 24s. Now I got to do 60. So 1 and 60. 2 and 30. How about 3? 3 and 20. 4? Can you go to 60 divided by 4? 15. 5? It ends in a 0, guys, so it's got to be 5. 5 and 12? Any more? 6? 6 and 10? Any more? 7? No. 8? No. 9? No. I don't have to go any farther because I've already got 10. What am I looking for now? Which one's the biggest they both got in common? They both have a 12. So, we all agree 12 is the answer to this. Yes? What is the problem with this method? It's very messy. Would it also be super easy to miss one? It'd be super easy to go, oh, I just forgot 512. Like that was just one I forgot, and I wouldn't have gotten the answer. Here's a better way. A better way to do this, 24 and 60, is to do the prime factorization. What's 24 break down into? 2 and 12. 2 and 6. 2 and 3. So what do you got? You got 3 2s and a 3. Yes? Great. How about the 60? Okay, 2 and 30. You could have went 6 and 10, but whatever. 2 and 15. Okay. 3 and 5. So what do you got? You got 2 2s, a 3, and a 5. Okay. Once you have the prime factorization, GCF. Does anybody remember how to actually pull out the GCF? Greatest common factor. What does common basically mean? They both have. So you're basically saying, what do they both have? They both have, do they both have 2s? How many 2s do they both have? They both have at least 2 2s, don't they? Do you agree they both have at least 2 2s? This one has 3 2s, this one has 2. They both have at least 2. What else do they both have? They both have at least 1 3. Yes? Abby.
I'm getting yelled at for Sour Patch Kids.
Now what do you think I should do with that 2 squared and the 3? What is 2 squared? 4 times 3? You get the better. To me, that is a much, much better method. It's much less, it's more compact, it's more straightforward. You're not going to accidentally miss something. You're just going to do the prime factorization and go from there. So let's say I wanted to do 18x squared y, and how about 27 x to the third y to the fourth. We're looking for GCF. Well, in the GCF, you could do the x's and the y's right now. How many x's do they both have at least? They both have at least 2 x's. And they both have at least 1 y. The x's and the y's are already in prime factorization. That part's super easy. Now all you got to do is worry about the numbers. 2 and 9, 3 and 3. This is 2 times 3 squared. Yes? Do the 27. 9 and 3, 3 and 3. This is just 3 to the third. What do they both have in common? They both have at least 2 3s. So what's the answer? 9 x squared y. The x's and the y's are actually the easiest part of this because you don't have to break them down. They're already broken down for you. All you have to do is worry about the numbers, break those down. GCF is just what do they have in common. Basically, the difference is, last chapter, we figured out what numbers, like when we took this and we multiplied things together to end up here. Now we're taking these and we're trying to start breaking things apart into what multiplied together to get that. That's the whole idea behind this chapter. GCF, is this stuff pretty easy? Okay, everybody take a look at page 527. $527. Let's do number 2 together. Number 2 is just break down that 20. What are 2 numbers that multiply together to get 20? 10 and 2. Am I done? 5 and 2. Am I done? So what's the answer? 2 squared times 5. Done. Is that first section pretty easy? Prime factorization? Okay. Let's do number 10. 12 and 60. You got to find the GCF. Yeah. So let's do number 10. GCF of 12 and 60. What do I do with the 12? Break it down. 6 and 2. 2 and 3. What do you have? 2 2s and 1 3, right? Okay, how about the 60? What 2 numbers multiply to 60? If it ends in a 0, I always go 10. Because then I can just go from there. 6 is 2 and 3, 2 and 5, right? What do you have? 2 2s, a 3 and a 5, right? Great. What's the GCF going to have? They both have a 3, and they both have 2 2s, don't they? Great. What's the answer?
12.
12. Is 12 a factor of 12? Absolutely. 12 times 1 is 12. Are we good with these? Are we good with the, if we, like 13, 14, 15, if we start adding variables, x's and y's and those, does that make the problem any harder? It should not. It actually should, to me, make it a little bit easier most of the time. Because most of the time, when a book starts adding letters, they start making the numbers smaller. Because they think it's making it harder. But to me, they're not making it harder, and now they make the numbers smaller. A lot of times, those are easier. Okay?